or Maxwell equations. And then basic solutions to Maxwell equations, like plane waves, and properties of plane waves. And then I would like to go to say how materials respond to electromagnetic excitation. And in a way, how we describe, characterize those on the level of our language, the material equations, material relations, constitutive relations, let's say material relations. And then because in metamaterials, the very important thing is that the essential, in fact, the most essential thing is that somehow the response is special, complex, very, very strong, for example, or very, very not so common, not something that we are used to before, and how to create and generate and tailor that kind of materials which would have a desired and special and strong response. That means that we have to study the ways media respond to electromagnetic excitation, and especially then we have to characterize those by different concepts which are like quite fundamental, like isotropy, anisotropy. Let's spend some time on these because these are very important concepts. Even like we say bi-anisotropy. Then we talk about things like losses and passivity, dissipation. Let's say dissipation is an important thing. Because when electromagnetic fields interact with matter, there are also then energies transferred to some other, not only kept in electromagnetic form, but say to losses, and then we lose something from the excitation. And then another quite important thing, which is very technical and perhaps non-intuitive, is reciprocity. Then there would be something like, which is also another material response thing, which is very important in natural and artificial materials, which is the frequency dependence, or we would say like a frequency dispersion. Meaning that a medium can react strongly for a certain wave with a certain wavelength, but then if you change the frequency, then the response is different. That is called like dispersion. And then that is so important that there are certain fundamental and basic models with which it is quite natural and helpful to describe material responses, dispersion models, which at least the three basic ones have been mentioned, probably also there. The say Lorentz, so-called Lorentz model. Hendrik Anton Lorentz, you have heard this famous Dutch physicist who also has the Lorentz transformation, and which Einstein also was a very good friend of. And then the so-called Drude model. These are extremely important in metamaterials business. Drude was a little bit earlier, a German professor in the 100 years ago. And then a third one, which at least I always like very much, is the so-called Levi model. Also a very famous person, which is then, whereas this Drude is more to the describing the response of, say, metals or conductors or some other materials of that type, and Lorentz is then more of like solid state type of not so conducting, but there is a resonating response. But then Levi is a little bit different. It is so what we would call like a relaxation type of phenomenon, that some excitation happens and then it like exponentially goes away. But that is extremely important in media which have so-called polar molecules, which are so that they can polarize strongly, like liquids. And a very good example and extremely important is water, and that is so important material in our everyday life that it deserves to be analyzed. Well, this is already quite a big packet. Do you have any questions on this agenda? Is there some of your favorite topics you would like to go on? All right. But anyway, I mean, you are listening so kindly, so I just encourage you, if you want to interrupt and ask questions, so feel free to do so. All right. And especially when I start then explaining things, it may happen that I go too quickly, or too slowly. Then it is your responsibility to say if I do it quickly or slowly. Please welcome in. Yeah. Do you have your packet already? Everything? No. Oh, okay. Yes. Yeah. Right. Well, but anyway. But we do have a coffee. Okay. Coffee break is okay. Just sit down and listen. Great. So, as I mentioned, then I start with just defining the concepts we are playing with: electric field, magnetic field, and so on. Electric field I denote by capital E, like electricity. Yeah, and then my and many others like to denote the character, the fact that it is like a vector by putting a bar on the top of that. This is, some people do some other ways, but this is mostly our way in this course. Electric field, meaning it is a vector, it has a direction, it is like the force that is applied to a charge. As you know, Coulomb's law, saying that we have a point charge, and if there is a force in air, then we know that there is an electric field to the direction of the force, if it's a positive charge. And then electric field is, of course, a field, meaning that it is changing in every place. So it may change direction. Here it is to that direction, here it is to that direction, and the amplitude, the strength can change also. And that is, these fields, electric field is, of course, generated in statics by charge distributions. We have, say, a point charge here. It creates a radiating, or not radiating, but a radial electric field, which decreases with a certain amplitude to the inverse square law. And then if we have a more complicated charge, like a dipole, plus charge and minus charge of equal amounts, meaning that they like nearly cancel each other, which means that the electric static field is decreasing even stronger. But still there is a bit of dipole moment, meaning that they are not exactly at the same point, meaning that there is a angle-dependent electric field, static field. So this is the sources create fields. An electric field then, we might want to say that it is a function of